This is the result of one man's quest to solve the twin prime conjecture. As the video begins, we should clearly define the conjecture and convey why the solution, if upheld to be correct, is significant. Consider the natural numbers 1, 2, 3, 4, and so on. A prime number can only be divided by 1 in itself. Examples of such numbers include 2, 3, 5, 7, 11, 13, 17, and so on. The spacing between these special numbers does not seem to follow any known pattern, making the next prime hard to predict. However, their spacing is of interest regardless, in part because it is such a mystery. A pair of twin primes is simply a pair of primes whose distance apart is 2. Examples include 5 and 7, 29 and 31, and 41 and 43. The twin prime conjecture states there are infinitely many twin primes, or pairs of primes, that differ by 2. Despite having a good grasp on what these behave like for small numbers, no mathematician has shown how many of these twin primes there actually are. Can we count how many there are, or are they infinite? Finding a solution would put an end to thousands of years without an answer. Depending on the solution, it could have implications in encryption and interstellar communication. One day while writing in a notebook, I began to list the natural numbers, and when I ran out of room on one line, I went to the next line. It looked something like this. And rather than looking at primes, I began noticing non-primes. The non-primes shown are multiples of 2, and also multiples of 3. Traditionally, 2 and 3 are prime, but if we exclude them, then primes must exist in one of 4 columns. And this is where the patterns emerge. If we start with a multiple of 5, then the numbers directly beneath it are also non-prime every 5th position. Observe as we zoom out. No matter the column, the blue are all multiples of 5. And every 5th value is not prime. An interesting find, but is this the end? Or is it just the beginning? In this setup, every 7th position is a multiple of 7. Every 11th position is a multiple of 11. Same idea with 13s. With 17s, and so on. Once all non-primes are filled in, only that which remains are primes. This is a systematic approach to finding the next prime using equidistant spacing. It always finds the next prime because lower multiples are eliminated first. For example, by the time we reach 25, we already know it is not prime because of the multiples of 5. Extending the table into negative values reveals a stunning rotational symmetry. Columns 1 and 11 are connected. Similarly, so are columns 5 and 7. When we check the spacing again, even into negative numbers, the spacing between positions holds true. Moving forward, we can simplify the 4 columns into 2. Columns 1 and 11 are identical, except for their minus signs. Columns 5 and 7 are similar. As we isolate the unique columns, it is useful to think of them as keys. The equidistant spacing of non-primes are like the teeth of a key. They must all line up to create the final key, which unlocks the mystery of the twin primes. To simplify things, we will remove the minus signs. Nothing has changed in terms of divisibility, and so this is allowed. At this point in my research, my intuition was telling me to merge the keys, but I was unsure how to do so. I didn't want to ruin the spacing. And then I noticed the key on the right. It was upside down. So I flipped it around. I re-looked at the spacing between the 2 keys, and I realized I knew how to slide them together. By expanding the numbers apart, we can merge the keys like so. One key made from 2. And once again, the spacing is intact. Below is another picture of the same key. The lines indicate spacing. Blue numbers are prime, yellow are not. The number 1 is the center point of the line, and the 1 is also the shaft of the key. The teeth extend to the right and to the left. And notice how the twin primes are revealed as pairs on opposite sides of the 1, like 5 on the left and 7 on the right, 11 and 13, 17 and 19. It was at this point that I understood the next step. Turning the key. By rotating and superimposing the coloring, those still in blue are twin primes. Those in green are a mixture of primes and non-primes. The yellow are pairs of non-primes. This creates a double sieve, the left half mirroring the right half, and can be used to find the number of twin primes. This is a proof that the twin primes are infinite. If we look at the right half of the double sieve only, since the left half now mirrors the right after turning the key, let's assign a 1 to the places where a twin prime cannot go, and a 0 to a place where it could go. By indicating this for each potential prime separately, and then stacking the various components vertically, we obtain the following. The vertical columns of all zeros at the gaps where twin primes of the form 6n minus 1, 6n plus 1 reside, where n is a natural number. If we can show that there are always new gaps emerging, then the twin primes are infinite. Using an infinite sum, this is indeed possible. As we consider how to construct an infinite sum, we must plan our steps carefully. The route I found easiest to take is this. Begin with the column on the left in yellow. Split the sequence 5, 7, 11, 13, and so on in half to create a pair of linear sequences. The first sequence is of the form 6n minus 1, and the second sequence is of the form 6n plus 1. By choosing this route, we avoid a sum with an oscillating term that would conceal if the sum will converge. From here, we need to take things row by row for each of our two parts. Beginning with the first sequence, 5, 11, 17, 23, and so on, count all potential gaps or zeros in the row generated by 5, and subtract out the failure of gaps or 1s from rows 11, 17, 23, and so on. If we were ever to arrive at a solution of 0 for a finite sum using this technique, we would know that we've run out of places for the twin primes to fill in. Conversely, if the difference is 0 or greater only for an infinite sum, then there are always gaps available for a new twin prime. The number of potential gaps in the first row as we tend to infinity is 3 over 5. Another way to look at this is we have 1 minus 2 over 5, which would represent a row of all zeros, subtracting out the first row of 1s. As we move on, we subtract out new 1s, specifically ones which were not previously accounted for above. If we double count the columns, where the ones have already been subtracted, we will gain an incorrect count. If counted correctly, there are 6 over 55 new columns which receive a 1. When we write out the two terms we have so far, we get 3 over 5 minus 6 over 55. Continuing on, we should get a count of 54 over 935 for the next row in sequence. As we gain more terms through observation, we see the following pattern come about. The bottom of the fraction is built with a finite product, and its beginning terms are 5 times 11 times 17 times 23 times 6n minus 1. The top, which is also built with a finite product, is 2 times 3 times 9 times 15 times 21 times 6n minus 3. When all written out, the first part of the equation looks like this. The result is 0 for the infinite sum, and the partial sums are all positive. And so we have a good start to the proof. To complete the proof, we must construct a similar sum for the second sequence, 6n plus 1. This time we start with 5 over 7 positions available. For the fractions we subtract after this, we obtain 10 over 91 minus 110 over 1729, which can be generalized in a similar manner to the first sum. The equation for the second half of the double sieve looks like so. We also get a value of 0 for this sum and a positive partial sum. When combining the two parts, we find something spectacular. By adding the two parts, we obtained an overestimate for the partial sum. When subtracting the two parts, we obtained an underestimate for the partial sum. This is directly related to how the ones align between the two sequences. But regardless of the estimate, when we extend out to infinity, 0 plus 0 is the same as 0 minus 0. In light of this evidence, it is my conclusion there are always gaps for the twin primes to fill into. This ends the proof.